Hi, I'm Leo, and I'm going to talk to you about urns, a data structure we developed with Antal and Kenny at the University of Pennsylvania. Now, most of you have probably taken an introductory probability course at some point or another, and some of you might have even encountered problems such as these. Suppose you have an urn containing 2 red balls, 4 green balls, and 3 blue balls. If you take 3 balls out of the urn, what is the probability that 2 of them are green? Problems such as these are part of a larger class of problems that involve sampling from discrete distributions. And the question that we're going to deal with in this talk and in our paper is what an efficient and persistent representation for such distributions is. Before I go into that, though, here's what I mean by discrete distributions. Mathematically, a discrete distribution is just a set of pairs of positive numbers and elements drawn from some domain A. For example, the distribution of the urn in the previous slide can be represented as 2, red, 4, green, 3, blue. How does one sample from such a distribution? The easiest way would be to draw a number uniformly from 0 to the sum of the weights, and then use that number to index into the set. For example, if we choose the number 5, then indexing into the set means that we would pick green to draw out of the urn. What I have described so far naturally gives rise to a simple list representation. If we put the pairs 2, red, 4, green, and 3, blue in a list, then we could figure out the total weight by linearly traversing a list and calculating the sum, and then indexing into the list in linear time as well. This representation is, for example, used in QuickCheck's frequency combinator, and I'll get back to that later. Now, this representation is fast for small lists and simple, and arguably good enough for most practical purposes. But it doesn't really capture what we want to do in our word problem, right? Because using a list is pretty good at drawing one ball out of the urn, but not really if you want to keep updating the urn. Like if you want to draw a ball and then draw another one, updating the distribution, the linear time traversal overhead would be compounded to a quadratic one. So it's not really a question of sampling from discrete distribution, it's a question of sampling from updatable discrete distributions. What do I mean by that? Here are 3 operations that we need in order to address the previous problem. We need insert, which lists do extremely efficiently. You just tack on a pair in the top of the list. We need sample, which by which I mean draw a marble from the urn and put it back in, or sampling with replacement, which using lists would be done in linear time. And remove, by which I mean drawing a marble out of the urn and keeping it out, which happens in linear time, again. In this talk, I'm going to present urns, a data structure for logarithmically performing all 3 of these operations. We have implemented this data structure, and it's currently on Hackage if you want to play with it. So, what is this urn? Here is a discrete distribution, a pair of random numbers and characters. And of course, as you might have guessed, since we want to achieve logarithmic running times, we're going to put everything in a tree. Now, the first thing that we need to do in order to sample is to actually calculate the total weight. So in order to do that, we're going to store cumulative weights around in every node. Now, the weight in each node represents the total weight of all leaves on the urn. So for example, that 9 over there on the left is the total sum of the first 4 elements, and 21 is the total weight of everything in our urn. In order to sample from this urn, we're going to first sample a random index between 0 and 21, say 14. Then, in order to figure out what element of our distribution that belongs to, we only need to look at the weight of the left node. We compare the 2, and since it's greater, we are going to go right, because the index 14 falls out of the entire weight of the left urn. In addition, we're going to need to subtract the weight of the left urn in order to make the index valid for the right subtree. Continuing in this process, 5 is less than 7, so we have to go left, and no index update is necessary since it is a valid index for that subtree. Finally, we're going to compare the last index with a leaf, and we're going to return that we sampled 5. And everybody's happy. Okay, now this sampling process is going to be logarithmic only if we are keeping the tree balanced somehow. And to deal with that, let's forget the fact that we want to do removals at some point and only deal with successive insertions and sampling. So I'm going to insert those 6 elements into an urn in order and see how we can keep the tree balanced all the time. Now, the key intuition that we have and the key idea behind pretty much everything is that we do not care about the order of things. Unlike search trees, where during insertions and removals we have to do elaborate rebalancing and preserving the order, here we don't care about that at all. It doesn't matter if 1 is first or 6 is first. The only thing that matters is that we have all of those elements in the list, in the data structure. In addition, as I'm going to be inserting this, I'm going to keep track of the urn size in terms of the number of leaves. We start, we're urn, single element, nothing to do. Then, when we insert the second one, we're going to create a node. The only choice we had here is whether we'll send it on the left or on the right, but that doesn't really matter. So, for the sake of convenience, we're always inserting things on the right when we're creating a new node. In order to figure out where we're going to do insertions from now on, we're going to look at the binary representation of the current size. So if the least significant bit is a 0, that means go left. If the least significant bit is a 1, go right. For example, the least significant bit is a 0, so we're going to insert 3 on the left part. So the 3 is going to be inserted where the 1 was, updating the weights accordingly. On the other hand, since now the least significant bit of the size is 1, that means we're going to go right. So the 4 is going to be creating a new node on the right-hand side. And moving along, if we repeat this process a few times, the least significant bit is the one that we take into account first. So the first 0 there means that we'll go left first. The second 0 means that we're, again, going left. And then for the 5 will be inserted where the 1 was. On the other hand, as you might have guessed, 1 means we go right, 0 means we go left, and sorry. And this way we have we can repeatedly keep inserting elements, keeping the tree practically maximally balanced. And all sampling operations on at any point are logarithmic in the size of the urn, which is what we want to accomplish. But what about removals? Okay, and here I want to remind you that by removal I mean sampling an index, following it down, and updating the relevant number to decrementing it by 1, decrementing the weight by 1, as if we were removing a single marble out of the urn. Okay, let's do that. Index 14, like we had in the beginning. 14 is greater than 9, so we go right. 5 is less than 8, so we go left, blah, blah. And we figured out that we want to sample and remove 6. Okay? Update its distribution, update the weights, fine. So what's the problem? Well, the problem comes when we pick index 0 in this case. What happens then? Well, following the sampling procedure that I have described, we arrive at 1a. Now, we have to update that and updating the weights. But now that 0, a is inaccessible. No matter what index you choose, no matter what you choose, you can never arrive at that 0, right? Because there's no number that is going to say that I, that is going to be less than 0. So it's always going to go on the right subtree here. So, and we don't want that. If we kept doing that, eventually we'd have a lot of garbage in terms of zeros that would affect our running times. So what can we do? Well, we could just delete it, right? Well, not really, because now we have invalidated our insertion scheme. It's no longer clear where the next insertion is going to go when we don't keep that. Worse, if we do a lot of deletions that happen to be on the left-hand side, the tree will again be unbalanced and our asymptotics just don't follow. So once again, I'm going to remind you that we do not care about the order of things. Yes, we cannot delete this 0, a, but there is exactly one element that we know how to delete, namely the last element we inserted. So what we can do is delete that element, updating the weights, and then eventually replace the 0. Ta-da! Everything is removed and our insertion scheme still works. So to sum up everything so far, I've shown you how we can sample, insert, and remove in logarithmic time. In the second part of my talk, I'm going to talk a bit about how we evaluated our implementation. And I'm going to do that in 2 case studies. The first one involves just sampling out of constant distributions that do not change at all, which is exactly what QuickCheck's frequency does. And I'll get to that in a bit. The second is actually the motivation for our line of work and involves randomized backtracking search. First one. This is the signature of QuickCheck's frequency. For those of you that don't know, QuickCheck is a property-based testing library that allows you to build up generator combinators from smaller parts, and frequency is arguably one of its most expressive ones. What it does is take a list of pairs of integers and generators and pick one of the generators at random based on that discrete distribution. Here, gen is a monad for randomness that QuickCheck introduces. Naturally, this brings in mind the sample that I showed you before. And as a side note, the fact that we want to put generators in an urns means that generators don't have an OR or an EQ instance. So we couldn't have exploited, we couldn't have used a binary search tree or an AVL tree that crucially rely on ordering for the elements. We can't have a constraint on our urns. So, okay. What's the experiment we did? We generated lists of numbers. So when you see n is 1,000 here, we have an input list of 1,000 different numbers, all with weight 1, so it's a uniform distribution. And we used both frequency and urns to sample 10,000 integers from that. And obviously, you can see the asymptotics here. When you increase the size of the input list to something that is probably impractical, urns dominate. Like, we can clearly see the asymptotics. But what we're really interested in is, what's the running time, what's the constant factor, what's the constant overhead of this logarithmic process I had described? And if you zoom in on that left part, so now we only look at lists between 0 and 25, you can see that even in very small lists, urns have practically no constant overhead. And in fact, starting from lists of length 10 or so, we actually start seeing small gains. So to sum up, the asymptotic behavior is, as expected, better, but there's no constant overhead for sampling even in small cases. And this is for the static case, which we didn't design it for this case. We designed it for the updatable case. Now, to evaluate backtracking, I'm going to turn into a case study that was mentioned once before during ICFP in Jan's talk on effectively quick checking compilers. What we're going to do is generate simply typed lambda terms that have a specific type T. This was done by Pauka et al. In 2011. What did they do? Well, there are a bunch of typing rules that can conclude T, and we view them as generation rules. Pick one of them and try to recursively satisfy the premises until we have completed the generation. So, for example, we can pick the var rule in order to generate an integer, and if we have a variable x whose type is integer, then we can just pick it and complete our generation. But if we don't have such a variable available, we have to backtrack a bit and instead use a different rule, perhaps integer. We can always pick an integer, so we picked 42, and we concluded our generation. So where do urns come in this picture? They come in the selection process. Basically, the original paper had a method of expanding weights and using permutation by sorting to select amongst the typing rules. Well, we just put all the typing rules in an urn and select one of them. I'll expand a bit on what the Pauka method was. imagine you putting all the typing rules, or every generator based on those typing rules, which I here represent as tvar and tint, into a list with some weights, say 4 and 2 for var and int. Then what they do is expand each rule in as many occurrences as the weight that is corresponding to. So we have 4 occurrences of tvar there, 2 of tint, and so forth. Then we perform a random permutation, a uniform random permutation that we can do in a bunch of ways. In the paper, they use permutation by sorting, generate a key and then for each one and sort accordingly. We could have used Fisher-Yates or whatever. And then we keep the first occurrence of each element, of each typing rule, in order to do a shuffling that allows us to pick rules in one order. On the other hand, you could just put everything in an urn and repeatedly remove things until you achieve the same effect. For our comparison, for our purposes, the Pau et al. Shuffling works pretty well for small lists, but it has a problem. It's pseudo-polynomial in running time. If I had made that 4 and 2 into a 40 and a 20, I would have to permute a 10 times larger list. And in fact, for the same exact distribution, we could have urns be arbitrarily faster than an equivalent use of the other algorithm. What we did, though, is just take their code base, like 1,600 lines of Haskell, change the 5 lines that involved the shuffling algorithm with an urn-based similar algorithm, and we already got a 2x performance. And that is changing a small data structure in what is clearly not the overhead in a huge development that deals with polymorphic unification and other crazy stuff in there for generation. So this was actually really nice. Other things that we have in the paper are a linear time construction algorithm. So instead of inserting things in sequence and achieving an n log n time, we can just linearly construct one from a list. A lot of more related work. Of course, lists are not the only thing that we can use to represent such distributions. So there are things like vectors in the random foo package or binary random access lists from Okazaki that are reminiscent. And we have even more experiments drawing again from the random testing literature, such that the information flow control experiments that we did a while back. Finally, the code is freely available on Hackage. You can play around with it and use it. Thank you.
Thank you, that was a great talk. If I understand right, your insertion into urns inserts all the representatives of a given value in one go. And if you wanted to add one more red ball to an urn that already has red balls, that's more difficult because you have to find where the reds are in the tree. Do you have any way of handling that?
Basically, there are 2 ways of handling that. One is to just insert as a different node, in which case removal would be a bit fuzzy, right? You could either remove one instance of there or one instance of there. If you were going to just remove one ball out of the urn, like turn a 6 into a 5, or in your case, a 5 into a 4, a 1 into a 0, that would be exactly the same. But if you wanted to do the thing we do in the backtracking search, where you remove all occurrences of something at once, right? If you choose a variable, you don't want to keep choosing the variable rules, then that would have a different effect. So that's one thing. The other thing you could do is add the different linear time insert, which is not optimal, but would achieve exactly what you're describing. Just add an AQ instance and look through the list, through the urn, insert it there, and update the weights.
So for deleting, are you storing the previous location of the last insertion so that you don't have to traverse twice?
We still traverse twice, but it's still a logarithmic traversal. And I don't know if you mean by storing, the last insertion is stored in the size of the urn. It's the binary representation of the current size minus 1. So one subtraction, one decrement something by 1, and then just follow the shifts.
There's quite a bit of mutation in your algorithm, so I wonder how it works in Haskell.
Sorry? There's no mutation in our algorithm. It's fully functional and immutable and persistent. You can keep different things.
Azure is different.
Yeah.
You stressed persistent.
Yes.
But in all the examples you gave, it didn't really need to be persistent. Do you have other algorithms that would, the persistency of the useful?
It's that information flow control right there that I didn't talk about. So there's a backtracking scheme in which you can actually, sorry, let me take a step back. What I just described in the here is essentially a randomized DFS, right? So you do a random permutation of your choices and go through them lazily. There were cases in other random testing that we wanted to sort of backtrack in a previous iteration, like not fully backtrack all the way back or only one rule, but access a previous iteration of the urn. So there we used a bit of persistency, but it's very niche.
I'd like to revisit the issue of removing a node whose weight goes to 0. So when you discussed that, you pointed out it wouldn't be any use to promote the sibling node because that would be in the wrong place concerning its binary path from the root. But I didn't understand how it would be okay to move across the last inserted value because its binary path might not be right either. Can you help me?
Yes, yes. Okay, let me revisit that a bit. Now, when I was doing the insertions, there is exactly the size of the urn dictates the path, right? So the next insertion here is going to be left, right, and it would go there, and so forth. But now, if I, sorry. Animations are good, but not when you have to backtrack. Now, if the next insertion needed to happen like where the 5 was, that would have invalidated our scheme. However, when I move the last element I inserted all the way there, the next insertion we know is going to happen exactly there, right? So while previously future insertions might have accessed this location, this is exactly the same urn as if I had inserted those 5 elements in sequence. So the next one just keeps going.
Oh, just a comment. Exactly the time algorithm that when you are doing that, and then you also use last, but then that was removed and blah, blah, blah. In this case, you don't need to bubble.
It's similar. It's very similar logic, yeah.
Okay, over there. So you have constant logarithmic time to sample an element. Logarithmic. You could think that if one element has very high probability, let's say more than half, up and down, that would have better average. So Huffman algorithm comes to mind.
Yeah, exactly. We were thinking about that. In fact, the only case where urns can be worse than frequency is where you have an example of like what you said, like one element with weight 10,000 and then 10,000 small elements with weight 1. In frequency, that would be many axes of the fourth element of the list, while in the urns case, every element has equal access time, roughly, no matter its weight. So in order to do that in a static case, we could use Huffman encoding or something like that based on the weights, but then we would need something like dynamic Huffman encoding, and we discussed that a bit in future work on the paper, but nothing concrete.
So with this removing, sort of the obvious way of doing it, you have 3 traversals of the tree, right? You want to look up first and be like, oh no, and then one to go back and delete it, and you have to change something over there, and then one to replace it. You actually get it down to like 2
we provide different operations in the paper. We provide sample exactly as I showed you and insert. The remove we provide actually removes everything from the bucket, so it doesn't just decrement one. And that can be done in 2 passes because you look up the last element and the one you want to sample. And we have update, which can do 2 or 3 depending on what's going on. So we have optimized in the usual case and sometimes in other cases.
You're using least significant bit first, then higher bit
Yeah, yeah.
and so on. If you use the reverse, you would essentially fill this array from left to right, I mean, looking at the bottom row.
Perhaps, I haven't tried that.
And, that could improve cache locality and maybe presentation.
So it So Antal over there, one of my co-authors, has actually checked the thing, and it results in fewer machine instructions. So that's why we picked that one. Simon.
So it's like in terms of the earlier question about adding more. So you can imagine an early which you repeatedly put things in, and you take things out, and you put more things in. Just this sort of persistent process. So unless if you had, so I guess this is a challenge, right? So you're saying, well, we could revert to a linear algorithm if we had GPUs, right? So supposing you had ordering or hashing on the other hand, could you both get your loop balance and loop performance that sort of somehow switch together? Multiple A's that you kept taking out and putting back in.
Yeah, the idea that we had on that is to keep a separate index, like another tree on the bottom side that allows linear indexing there. And that could work if we added ordering. It's just that we didn't have a use case for that, so we didn't bother doing it. But I can very well, if someone has a use case for that, it shouldn't be too hard to implement. We have a quasi-quoter for that. We can, if you know the element, we can use template Haskell to basically construct the list if you give us a from list algorithm that takes a concrete list, can construct the list at compile time effectively. So we use that. And that's exactly what the linear time construction algorithm that I didn't show does. It exploits the fact that we know the structure of the list to construct the urn. The sequence of elements in the urn is not the same that you would get by doing a sequence of insertions, but we don't care about the order.